Welcome to the first real lecture of artificial intelligence. The last one was more of an introduction how the course would go. So in this lecture, we will be looking at what artificial intelligence is, and we will go through some of the historic definitions of artificial intelligence, and then look at what is a more modern approach to artificial intelligence. All right, without further ado, let's go into the slides. And first, we have one of the very first definitions about artificial intelligence from Alan Turing, which he came up in 1950s. So we have to keep in mind that in 1950s, we didn't have computers. So this was theorized before even the computers were a thing. So this was based on the thought experiment called the imitation game, where an interrogator will be questioning a man and a woman and will be trying to identify who the man is and who the woman is solely based on their responses. So typically written responses. And similarly, Turing proposes that if an interrogator, shown as C here, can identify who amongst A and B is the computer. Well, if C cannot identify who is the computer amongst A and B, or rather we can say that if A can convince the interrogator that it is not a computer but it is human, then that is true artificial intelligence. And this attracted quite a lot of criticism in the years to come, but this was quite an interesting test for artificial intelligence. And many of the robots or AI we see in movies and TV series, books, and so forth have AI pretending to be humans. So this has been quite a famous test in popular culture. You can see in Terminator, the Terminator pretends to be human, or what was that one? Westworld. I think Westworld is the TV series where there's a confusion between who the AI is and who the humans are. So this was a really famous test to decide whether a machine is intelligent. So the criticism came from the fact that this is trying to imitate human behavior, but not just trying to be intelligent. So humans, are we always intelligent? So I would say that no, we are not necessarily intelligent all the time. A typical example is making typing mistakes or grammar mistakes, language errors, etc. So that's not necessarily intelligent behavior. Or we can have like even more deep unintelligent behavior in humans. We are destroying the planet we live in, and we elect not so good politicians, and humans in general do a lot of bad things. They make a lot of bad decisions. So there is an unintelligent side to humans, right? So, and then we have the other side, like there is intelligence that humans cannot perceive. There are some things that humans are basically unable to perceive, like that intelligence could be found elsewhere in the world, or there could be forms of intelligence that we can't see, or because we can't understand that it is intelligence. So this is why Turing test has been criticized. So think about this a little bit while we move on to another early definition or another thought experiment into artificial intelligence. So this was a Chinese room argument brought forward by John Searle in 1980s. So here we consider a Chinese speaking machine that passes the Turing test. So according to this thought experiment, there is already an AI which passes the Turing test, but this is for some reason a Chinese a machine. So what happens now is an English speaker goes into a room, a confined room with the machine, and accepts the input, then processes it through the Chinese Turing AI, and then outputs or like passes on the output. So like we have a room like this, you get the input, and we have the human, then we have the Chinese machine. So the human gives the input to the Chinese machine, then the Chinese machine gives back the output, and the human gives the output back to the outside of the room. So in this scenario, a Chinese person will accept that this is an intelligent human, but the human inside is not necessarily intelligent. What they do is they just pass it on to a machine and takes it back and presents as their own. So what Searle wanted to show is that if a machine is just following some instructions or just step-by-step instructions or a set of rules, etc., then is it really intelligent? Just like the human does not understand Chinese, so we can say that the human inside the Chinese room does not understand Chinese. Just like that, the machine also does not understand. It knows how to replicate or to imitate. So that also can be argued as not very intelligent behavior. So now this brings us to the question, so what is intelligence? So I think we discussed already, are humans intelligent as a species, as individuals? Questionable. And we discussed about unintelligent human behavior and also intelligent behavior beyond human capacity. So think of a couple of examples for intelligent behavior beyond human capacity, and maybe I will open a forum, so like you can post this ideas for this in the forum. Post in the forum. So I will make these notes with my annotations available as well as the slides. So there are these are some aspects of intelligence that we can think of. This is not an exhaustive list. There could be much more traits that we would like to see in an intelligent machine. So at the top we have reasoning or problem solving. So a machine should be able to reason given a particular scenario rather than following a set of rules. It should be able to solve a problem or to reason what is the best to do in such a scenario. So we see some things, some examples of these in the modern world. Self-driving cars are sufficiently okay with this, but like still we hear like some self-driving cars running people down and stuff like that. So see, there's room for improvement. And knowledge representation. So it's not just enough to learn, but we should convert that into knowledge and represent it so that we can access it at a later time. So can machines do that? Some machines can, in up to an extent. Planning. This is quite done already, like route planning in Google Maps is a very good example. And then learning, there's a lot of machine learning algorithms that you guys may already know of, and a lot of applications. Machines are known to learn representations about certain animals. Maybe you have heard of the cats and dogs example, where a machine learns to distinguish between cats versus dogs. And then natural language processing. This in particular is not a big thing anymore, but still quite important, because you see machine translations everywhere. It's like pretty much standard. So that's another thing with artificial intelligence. When things we think are intelligent uh, become more mainstream, we tend to think, oh, like that's like pretty much expected, not really intelligent behavior. So because going by some of the original definitions of machine intelligence, just adding two numbers would be an intelligent thing to do. So yeah, so natural language processing, then perception, like seeing something or hearing something and understanding what's going on. Motion and manipulation, this is more into robotics. An intelligent machine can move themselves or manipulate something. So maybe you have seen videos of, how like there are little like check boxes on websites saying I am not a robot. Have you seen actual robot arms? Sorry, I'll just move myself a little bit over here. So there are actual robot arms that can tick these things and manipulate someone into believing that it is a human. So maybe I'll check the video for this. It's just funny. And then social intelligence. I mean, some humans don't have social intelligence at all, but some machines try to have social intelligence. It knows how to talk to different people differently, and I don't know what else is there in social intelligence. Something for you guys to think about. And general intelligence. So this is an important part of it. So general intelligence means rather than being specified to do something, an AI is a good intelligent machine if it has general intelligence. It can do many things. It can learn a language and translate. It can look at a cat, images of cats and dogs, and identify what are the cats, what are the dogs, and it can plan a route. So generally, like as humans, we are able to be intelligent in many aspects of everyday life. So a truly intelligent machine should be able to do a lot of things, not just fun. So we will discuss a little bit about this general intelligence when we go into neural networks. You will see that how we can sort of identify general intelligence behaviors in neural networks. And yeah, so this is again something quite interesting, I thought. Then we come to this question of weak intelligence versus strong intelligence, or weak versus strong AI. So if you don't know, this is Arnold Schwarzenegger from Terminator, and this is Siri. I think most of you know what Siri is. So it's an assistant on Mac or Apple operating systems, like Hey Google or Alexa. So anyway, so the idea behind weak versus strong AI is that a strong AI is a generalized AI. A strong AI has generalized intelligence. It can do many things, like Terminator does. And Siri, for example, can only do very limited amount of tasks. So Siri is a weak AI in terms Siri knows how to do a specific thing, like it knows how to search Google or like do a calculation, make a reminder in your calendar. So things like that. But a strong AI, on the other hand, is much more capable. It can move itself, it can manipulate, it can do many things. It can time travel in case of Arnold Schwarzenegger. Anyway, so I have left a link for a Forbes article discussing this strong versus weak AI. I think you'll find it quite interesting. So have a read. And next, we are going to look at a few distinctions. I thought this is a good thing to look at before we go into a modern definition. So we talked about AI, but where does machine learning and deep learning fit in? So artificial intelligence is like human-like intelligence. I wouldn't say human intelligence, but similar to human intelligence coming from machines. It's not very specific. It's a very broad area. While machine learning is specifically an approach to artificial intelligence through data and algorithms. We use data so that machines can learn. So there's specific forms of knowledge representation in there, specific forms of learning, and this is like more with data, like data science and machine learning always goes together. So ML is a data focused approach to artificial intelligence, and deep learning is even a more specific technique for implementing machine learning, specifically through multi-layered neural network. So we will be talking about this at our neural network lessons later in the semester. So something I'm going to leave you all to think about is, why are we more interested in machine learning and deep learning nowadays? And I'll make a forum topic for this as well. There's a lot of forum topics. I expect you to participate, and at the end of the semester I might award some of the continuous assessment marks for forum participation. So yeah, I'll make this a forum. And another blog post by NVIDIA. This is where I got this nice graphic explaining the differences between AI, ML, and deep learning. So please do have a look at their blog as well. Now we are going into a more like modern, like still like 20 years ago, a more modern approach to artificial intelligence. Here we are not very specific in a way. We say computational intelligence is the study of the design of intelligent agents. So we are studying how to design intelligent agents. So we don't really specify what intelligent is. We say that an agent, if an agent is able to perceive the environment and act on it, that is an intelligent agent. So the better they act, the more intelligent they are. So this is a very open ended definition which allows us to use it in many situations. So I quite like this definition. Not sure whether this is in the prescribed textbook, or which I forgot to mention in the introduction slides, but it is there in your learning management system. So please do have a look at it. So this is not in there. I don't think this definition is in your textbook, but you can use this definition because I am including it in the slides. And yeah, so we mentioned a couple of other points here. Agents have objective functions. So an objective function is where an agent has an objective to achieve, and it can measure the achievement of that particular objective as a function. So agents know how close they are to their objective, and they perceive the environment. They can see what's going on in their environment. And agents use prior knowledge, or learned knowledge. So they act autonomously based on their knowledge, based on the perceived environment, to improve their standing according to the objective function, right? So, for example, a self-driving car has knowledge of the road rules. It can perceive the environment through the cameras and various sensors, and it has an objective to get to a certain place. Let's say that like you are driving to the university. So agent will act autonomously. The car will act autonomously to improve their standing compared to the objective function. So you need to get nearer to work, so the university. So it will do that, but not like destructively just driving anywhere, just not driving on a straight line. It will perceive the environment, identify the path, use knowledge about things in the environment, the road rules, etc., and take you to the university. So this is an example on how intelligent agents could be used as a definition for artificial intelligence. So any of these definitions are fine. I don't require you to memorize definitions, just have an understanding of this is what intelligent behavior is. All right, now we are going to look at some types of agents introduced in this Russell and Norvig paper. No, sorry, this is a book. This book, I have included a link to the book. There's I think there are some chapters available. If not, I'm sure you can probably find this book somewhere on the internet. Yeah, I think I have included a chapter from this book in your extra readings. I think chapter 2, it's quite interesting, so please have a look at that, and we'll go through these different kinds of agents. I think this one is not from this, but this is a more modern version of the agents from Russell and Norvig classification. So these 4 are from Russell and Norvig chapter. Like you can have a look at that, but we'll go through some of them. So a simple reflex agent is, as the name suggests, is quite simple. You have the environment. The agent always have sensors and effectors. So sensors perceive, effectors act. So when the agent gets to know what the world is like now, it has some condition action rules, very simple rules. If this, do this. If A, do X. If B, do Y. Like that. They have a rule table. Then based on these rules, it acts. Perceive, decide the action based on the set of rules, then act. It's very straightforward. Then we have agents that keep track of the world. This is as earlier we perceive, but we also are informed from our previous experiences. So we just don't forget what we experience now. We have a memory of what happened earlier. So based on that, we can make a better decision, but still with just condition action rules. So a little bit better because it allows you to have agents who are aware of the history. And history, knowing history is supposed to make you more intelligent, right? Because you will not repeat your mistakes. So this is exactly what this agent will be doing. And then we have goal-based agents, like the car, autonomous car I mentioned earlier. This agent has a goal. It has the ability to perceive and is informed with previous experience. Like it knows the road we have come so far, what happened so far, how that particular driver in the red Honda is behaving. So like some stuff like that. And it has a goal in mind. We need to get to the university. And then decide on the action based on the ability to reach that goal. So this is a more like motivated agent. Like it's not just roaming around. It knows that it has to achieve this goal. So a little bit more intelligent, I would say. Then we have utility-based agents. I'll just go down a little bit. All right, so we have utility-based agents. Here, like we'll have to look at what utility means, right? So utility is sort of a synonym to like happiness or like comfort or a cost, some kind of associated cost or like a reduction of that cost. So in this case, the utility-based agent does all the things which a goal-based agent does, but also it has a sense of utility. For example, from the autonomous car example, it will take you to the university, but it's not going to go all around the city and finally end up at the university. It will take the shortest path, or it will take the path that takes the least time, the fastest route. So, see, like the difference between just being focused on the goal and having a utility function as well. So the utility function reduces some kind of a cost, or like keeps the agent in a more happier state. Happy is not very we can't really define that, so that's why we say, like, we call this the utility. So it will take the car safely there, like it will not ram into other cars, like, so like this kind of things. It does not blindly follow the goal. It makes sure that a utility function is observed. So I think that's it for this lesson. So this is like how a typical lecture is going to be, around 30 minutes. I'd like to think they're short and sweet, but if not, please let me know. And next time we meet through one of these videos. I'll be explaining to you some exciting uses of AI. So still another week 1 video. As I mentioned earlier, there's going to be 3 videos per week. So this is going to be the second video of this week, the exciting uses of AI, because we had an extra video introducing the subject, but I think you understand it. All right, thank you very much, and I'll see you later.